Hey guys, and welcome to the first quantum computing tutorial on this channel. Yes, you heard it correct. This is going to be a quantum computing tutorial. Uh, I know it sounds very weird that how could this happen? Like, how can I get access to a quantum computer? By the end of this video series, you will have understood how you can get access to a quantum computer for free, and it's totally legal. It's nothing like it's not that legal and stuff. It's provided by IPM. It's a service called Qiskit. I think a lot of you would have heard about this service. It's a very good service. I totally will appreciate if you guys also follow along with this video. Now, what I want you to do is first sign in into IBM Quantum Computing. It is required because if you actually want to create these quantum circuits and all of the quantum computing, if you actually want to use quantum computers in your daily life instead of your classical computers, you need to be having a Qiskit account. I went ahead created a Qiskit account. You guys can also do that. And yeah, so I'm over here. Let me just open up my PowerPoint presentation and let's just get started. So today I'm going to be explaining you quantum mechanics. One thing, I'm not a quantum physicist. I don't know a lot of quantum physics. I know a decent amount, like I know a lot of it, but I'm not an expert at it. So if you think that like in some areas my explanations are kind of finicky or something that you feel isn't particularly correct, please let me know in the comments and I will like fix it. Also, a lot of the things that you're going to be seeing in this video will be something very unusual, like you would be thinking this is not possible, but indeed it is possible. And yeah, that's what happens in quantum physics. It's just very, I would say, different from classical physics. So that's one thing. So so the first, right, what is quantum entanglement? I'm just going to play it. So, quantum entanglement is caused between two quantum particles in this type of a quantum system. The particle exhibits a spin up or spin down state. So basically, I know you didn't understand the word that I've written over here. Let me explain to you. So, if you know any basic chemistry, you know that an atom is built up of like three like subatomic particles called electrons, protons, and neutrons. The protons and the neutrons are like situated inside the nucleus, while the electrons are revolving around the shells or the orbits or the energy levels of the nucleus. Now, the thing is, a proton exhibits a positive charge, a neutron exhibits no charge, while an electron exhibits a negative charge. Now, the thing is, this electron, they have a number of properties. So, I think we all know a lot of the properties, but one property is called the spin of the electron. Now, you might have not heard this property in like a everyday chemistry textbook, unless and until you are like a major in physics and chemistry and like you have picked up science. You probably would not have heard this term called spin. Basically, what the spin is, it's a value that is given to the electron. So each electron can have either of the two spins. It cannot have like two states in the spins. It can have either a spin up state or a spin down state, and the electrons will like and the thing is, the weird thing is, we don't actually know that which spin the electrons exhibit unless and until we actually look at it and we actually do a lot of the calculations and stuff. We don't know what the spin is. So that's one thing you need to know. Now the thing is, so that's what the spin is. Now the thing is, quantum entanglement. What quantum entanglement is, let's just say quantum entanglement always occurs in more than one particle. You cannot have quantum entanglement in one particle. So you should have like two particles. Yeah, you should have two particles to actually see quantum entanglement. Like you can't just have like one single electron in quantum system. So quantum system just stands for that electron thing. So you can't have that. So like if you just have a single electron, you cannot say like you are having a quantum entanglement. No, quantum entanglement means two electrons that are bound together. Now Einstein never fully accepted quantum mechanics. So if you are like a big Einstein fan and you have read a lot about Einstein and his discoveries, general relativity, special relativity, and all of that, you probably will find that Einstein really um, disagreed with the principles of quantum mechanics. He thought that quantum mechanics was kind of stupid. That's what he thought, that it just did not make sense. And actually, it was Einstein who did not like understand quantum mechanics fully, but that's the thing. So if you're like a big guy, like a person who is a big Einstein fan, you'll probably be seeing some points that uh, kind of like where Einstein gave some other interpretation, but quantum mechanics gave some other interpretation. But these ones are correct. Yeah. So the thing is, what quantum entanglement is. So there will be two particles, and those particles are going to be entangled to each other. Now there won't be any rope or chain binding them together. It will be like it's invisible. They are just bounded together. So what happens is these two electrons that are bound, the two electrons will always exhibit a spin that will be opposite to the other. So if the first electron in the quantum system exhibits a spin up state, the second electron in the quantum system will always exhibit a spin down state. But now over here comes the actual mind boggling and the crazy part, a quantum superposition. So the thing is, before the quantum entanglement particles are measured. So you will only know the spin of the electron, which I just told, when you measure the electrons. Before the quantum entangled particles are measured, they exist a spin opposite to each other. So this is called a quantum superposition. Now I think you might have said, hey, I just repeated the same thing over here. Well, it was a bit different. The thing is, in a quantum superposition, let me explain it to you better now. I think a lot of you will not understand what I'm trying to tell over here, even though I like break it down to like particles. Even though I will like explain you with the best possible way, it will be very difficult to understand what I'm trying to tell, unless and until like really high amount of mathematics and a really high amount of physics. If I think like nobody will be knowing this, but actually there's a chance that a lot of you guys would be knowing this, called the Schrodinger equation, so the Schrodinger wave equation. The reason why I'm telling that, a lot of you might be knowing this, is because it's like termed like one of the hardest equations in like physics. It's pretty difficult to solve in certain areas. It's unsolvable. So if you know the Schrodinger equation, this will be very easy for you to understand this. I'm not saying you to go and understand that equation. It will probably take you months to understand it. But like if you really want to understand the core features of quantum mechanics, you need to be knowing operators and the Schrodinger equation, and you need to be knowing a lot of those, the Ehrenfest theorem. Uh, you need to be knowing all of that. So if you want to understand all of this at a very deep level, comment down below, and I will like make a the second video will be detailed to like all of the people who are really interested in the mathematics aspect. But to understand the Schrodinger equation, you need to be having like a really good understanding of physics. Like you need to be knowing quantum mechanics. You need to be also be knowing operators and of that in quantum mechanics. You need to be having a really good understanding in chemistry, because I know quantum mechanics is like it's physics and chemistry bound together. So that. So what happens is the two particles, before measuring the particles, these particles exist a spin opposite to each other. So they it's very difficult to explain it. These particles exhibit a spin opposite to each other. Like the spin is not defined. Like the first particle will be exhibiting both the spins, and the second particle will be exhibiting both the spins. And when the first particle will be measured, the second particle will choose the spin opposite to the first particle. I know it sounds very insane, because those two particles can be like on the either sides of the universe. Like the first particle can be on the one end of the universe, and the second particle can be on the other end of the universe. And still, if the first particle is measured with a spin up state, the second particle will be measured as a spin down state. Cannot be like both the particles are of the same spin. It is not possible. So that's a quantum superposition. So I know it sounds very absurd that how can this happen, and that's what I really bamboozled Einstein. Einstein really thought that, and we all know that the threshold is of like the speed that we can travel is the speed of light, which is 3 into 10 raised to 8 rounded. So that's the thing. So the thing is, Einstein called it the spooky action at a distance. The reason why Einstein called it like spooky action at a distance is because if we look into it logically, the messages between the particles are traveling faster than the speed of light, which is really absurd. They are actually traveling at kind of like an infinity speed. Like, even if you can travel faster than speed of light, how can you travel at the speed of infinity? Just a second, guys. I'll be back. Sorry, guys. Just got a little phone call there. I had to attend it. So that's what a quantum superposition is. Now, that's why Einstein called it the spooky action at distance. Now, I know, like at that time, uh, even quantum mechanics could not justify itself pretty nicely. It's now that, like, with all of these equations and all of these brilliant scientists across the globe who have really kind of like simplified quantum mechanics and actually are starting to arrive at like kind of solutions. It's like we still have not got like a very good solid foundation of quantum mechanics. We do not have that, and we probably won't have it in the near future. But let's be positive. So let me give you an example on this quantum superposition, and yeah. So the best example for that is the Schrodinger cat. So Schrodinger was the one who proposed the Schrodinger's wave equation, and to make people understand quantum mechanics better, he proposed this kind of a beautiful example called the Schrodinger cat. So the Schrodinger's cat is a wonderful example of a quantum superposition. If a cat is placed in a box and some small container containing toxic chemicals is placed in the box, and if the box falls down, there can be a chance that the cat could have been killed because it would have inhaled the chemicals, or the cat would have survived because the box of the chemicals would not have broken. Before you open the box, the cat is in a quantum superposition because the cat can be in two possible states, either dead or alive. But after we open the box, we find out that the cat is dead or it lived. This is called measuring the quantum particle, which I just explained. Now, at this point, the first particle will assume the spin, and the second particle will assume a spin opposite to the first one. That's what I wanted to tell. So this is the entire Schrodinger cat equation. Now I now another example of this can be when a baby is about to be born. We don't know what gender the baby is in. Like, it can be a male or a female or like the other genders. So it's like now that there are therapies that we can undergo to get the genders, but like it's just an example. Like, that's the example. So you can see quantum superpositions happening in like everyday life, like you having like your test, and you are gonna get your results, and you can either get like these grades, so like either an A plus grade or an outstanding grade or like an A grade. So it's then a quantum superposition. It's then that you get the report card and you are like, okay, I got an A plus. So like the spin gets measured. Now these are like very simple examples. Like, quantum mechanics is much more complicated than this, but yeah. So virtual particles, I'm not gonna get into virtual particles and vacuum, quantum vacuum over here, because I feel it can be a bit off topic and also I think a bit difficult to understand. Now let's actually get into the computing aspect. I'm not saying the coding aspect, the computing aspect. Now, this is quantum mechanics in the physics. Now, what the computer scientists did is they were like, okay, so this is quantum mechanics, and what if we could do something like this? We could like make this in computers. Now, it was easier said than done because quantum computers are very difficult to make because all of the information is encoded in like those bits. Now, the thing is, classical computers, the smallest thing the smallest memory that a classical computer can have is a bit, so bit. And like it's like this: a bit, a byte, then it's a terabyte, I'm sorry, it's a megabyte, I'm sorry, it's like a bit, byte, kilobyte, megabyte, gigabyte, terabyte, and then it's like all of those really big things. So that's the thing, so that's how it all works. But the thing is, the in quantum computers we change the original bit to a qubit. So qubit is like the quantum bit. So what happens is in a quantum computer, the the bits that we have in like the bits is are like changed to qubits, and all of the parts. So the main quantum computer is not going to be that little rectangular silicon chip. No, it's actually kind of different in shape. They're like it's pretty weird in shape, and I think according to my research, the quantum computers are usually made up of phosphorus, because the all of the information is encoded in those atoms and all of that. So that's why I think phosphorus was like a very good element to do all of that on. So that's why they used phosphorus. I'm not like much of a expert at this, so yeah. So the thing is, what happens is, where would you actually use a quantum computer? That's a question that a lot of people have in their minds. That okay, we have the technology, but where do we use it? Now, quantum computers are in an early stage of development, and they're not that developed. Like they are pretty developed and still better than supercomputers, but they are still like very early in, like if you have a look at the quantum physics, like if you have a look at it. So the thing is, quantum computers can be used in areas where there are millions of possibilities. Let me tell you. So let's just say, you are running like a casino, and you have that the spinning game, like where you spin the thing. I don't really know what that is, but that's an example which a lot of people propose when dealing with the quantum computers. So they give the example of that casino, and what they tell is that in the casino, uh, like 5 people can play that game. Now the thing is, like there are 5 people and they can play that game. So the possible things where the and like all of there are 5 chairs and they can like spin around and sit on the ends of the table. So the possibilities where like each person sits is gonna be something X. But if there are seven, then the possibilities will increase greatly. But if there are 1,000 people, then the possibilities will literally be like in billions, if not quadrillions. And if the people are even increased, I think at one point it will be like the number of atoms in on the earth, or the number of atoms in the universe. Obviously that's like just an exaggeration, but that's the thing I wanna get to. So that's why we use a quantum computer. A quantum computer can do all of this in one go, and because of all of these mechanics, and get us. So that's why. So that's where you will actually use a quantum computer. Now the thing is, quantum computers are kind of expensive, and you won't really get one lying around in like a computer store. They are $100 million, I guess, 75 to $100 million, and only a few people own them. It's like, I guess, the IBM made it. Then there was also like other companies who made it. Then it was like, I think one person had bought a quantum computer once, and it cost him about $75 million. 75 million. Yes, these are not cheap computers. So these are not what you're gonna get on Amazon, or like any other store. So if you wanna use a quantum computer, you gotta get access through IBM services. You can't just go ahead and buy one. Unless and until you have like $75 million lying around in your pocket, you don't buy one. And plus, who knows whether you use it or not. So this is the best thing. So yeah, so that's what they're commenting computers. So that's why one thing I want to get done is actually, you know what, in the next videos I will probably get into the coding aspect of the quantum computers. I know it was like a lot for this first video, because like I know even understanding quantum mechanics is not that easy. I hope I've explained you guys that very well, because it is very very important that you understand this, because otherwise it will be very difficult for you to actually understand the actual quantum mechanics, like the quantum computers, those things that I've done over here, the quantum circuits, the all of these NOT gates and the C nots, and this code it will be, and all of this. I know sounds a little bit mind-boggling, but it's all right. And this was the same reaction I had when I first was introduced to quantum mechanics. I was like, what is this? So yeah, So that's it for this video. The second videos will be coming very soon. I know I hadn't uploaded for a little while because I was on a vacation, so that's why. But I'm back on track. So that's it for today, guys. I hope you enjoyed the video. If you did, like and subscribe to the channel, and I will see you in another YouTube video.